Now, a strictly stationary process with the first two moments finite will also be a second-order weakly stationary process, aka a covariant stationary process. However, the converse is not true. We see this in example 2.3 on page 9. We'll let Zt be a sequence of independent random variables that alternately follow a standard normal distribution, n 0, 1, and a two-valued discrete uniform distribution with equal probability 1/2 of being positive 1 or negative 1. So Zt alternates between being normal, uniform, and so on. Let's compute the expected value of Zt in these two alternating scenarios. If the time is related to the standard normal distribution, then the expected value of Zt, or the mean of Zt, is going to be 0, because that's the definition of the standard normal distribution. The mean is 0. If the time is related to this uniform distribution, with Zt having a 50-50 chance of being either 1 or negative 1, the expected value of Zt is again 0, because the average of 1 and negative 1 is 0. So regardless of which type of distribution the time point is related to, the mean of Zt is always 0. Let's look at the variance of Zt. We know that if the time point is that of a standard normal distribution, the variance of Zt will be equal to 1, because by definition, in a standard normal distribution, mean equals 0 and variance equals 1. Now, if the time point is that of the uniform distribution, how do we calculate the variance of Zt? Well, if you look at Wikipedia, you'll see an equation that says variance of x is equal to the expectation of x squared minus expectation of x quantity squared. So just like covariance is the degree to which multiplicativity fails, you can think of variance as also the degree to which multiplicativity fails. It's a special case of covariance, the variance. So here we have a mean of 0 in the case of a uniform distribution, because the average of positive 1 and negative 1 is 0. And we have a variance of Zt equal to the expectation of Zt squared minus 0, which just means variance of Zt is equal to the expectation of Zt squared. So what's the expectation of Zt squared? Well, Zt squared could be either positive 1 squared, which is 1, or it could be negative 1 squared, which is also 1. And there's a 50-50 chance of either of those happening. The average of 1 and 1 is 1. In other words, 1 squared multiplied by half plus negative 1 squared multiplied by half is equal to 1. So the expectation of Zt squared is 1, the variance of Zt is 1. So therefore, the variance is always 1, whether it's a standard normal distribution or a uniform distribution that the time point is related to. So therefore, for this process, your mean is constant, your variance is constant. Now let's look at the covariance. We'll pick two time points, which we'll call time t and time s, and we'll look at the covariance between Zt and Zs. Now remember, covariance between x and y is equal to expectation of xy minus expectation of x times expectation of y. So here we have covariance between Zt and Zs is equal to expectation of Zt Zs minus expectation of Zt times expectation of Zs. Well, expectation of Zt is 0, no matter which type of the two types of distributions we're talking about. And expectation of Zs is also going to be 0. So that latter term just becomes 0. 0 times 0 is 0. And so you have covariance between Zt and Zs is equal to expectation of Zt Zs. If t is not equal to s, the covariance between Zt and Zs will be equal to 0. Why is that? It's because all the z's are independent random variables. Zt is a sequence of independent random variables. And independent random variables do not move together. They're not correlated. They don't covary. So covariance will be equal to 0, and the correlation between t and s will also be equal to 0 if t is not equal to s. Now, if t is equal to s, then Zt and Zs are exactly the same. So they're going to be perfectly positively correlated, and in this case it helps to look at the second equation at the bottom of page 9 before you look at the first equation. The second equation is the correlation equation, and in this equation we know that the left side of the equation is going to be equal to 1 if t is equal to s. Now, how do we derive covariance? the top equation? Well, we see that the numerator of the correlation equation is covariance. In the denominator, we have root of expectation of zt squared times root of expectation of zs squared. Since t equals s here, and the expectation of zt squared is equal to 1, that whole denominator just becomes 1. So correlation between t and s is equal to the numerator, expectation of zt zs. So correlation is equal to covariance in this case. And correlation is 1, so covariance is also 1 if t equals s. And you can see that the covariance does not depend on time, and the correlation does not depend on time. So therefore, the process is covariance stationary. So in this example, the process is a covariance stationary process. However, the process is not strictly stationary, and in fact is not stationary in distribution for any order at all. Why isn't the process stationary in distribution? Well, because you're alternating between distributions. Let's say t equals 1, and that t is associated with the normal distribution. If you add 1, now t equals 2. It's the next value of z in the sequence. This one has to be associated with the uniform distribution. Well, the normal distribution and the uniform distribution are not the same. The distributions are not equal. So therefore, the process is not stationary in distribution. So this is covariance stationary. However, it's not stationary in distribution for any order at all. And so, of course, it can't be strictly stationary either. So, now I hope you have a good understanding of the term stationary in distribution and the term covariance stationary.